Good. Hi, good afternoon. Is this on? Good afternoon. Thank you for joining us. Thank you for joining us today. Hello, we'd like to get started because we have many people watching through our live stream audience. Is it louder now? I'm Gina Vild. I'm the Associate Dean for Communications and External Relations from Harvard Medical School. And I'd like to welcome, I can't get everyone, I think he can't hear up the top. All right, we'll fix the acoustics. Can you hear in the top? Can you hear in the back? All right, no? All right. We will start again. Good afternoon. I'm Gina Vild. I'm the Associate Dean for Communications and External Relations for Harvard Medical School. And I'd like to welcome all of you here today, especially our returning students and our new students, and all of you who are watching from around the world on our live stream. I invite you to note on your calendars the upcoming talks at 12. On October 11th, we will have a talk on music as medicine. On November 8th, to launch our HMS Season of Giving, we will have a talk on the power of resilience. And on December 4th, we will have a talk on the flu. So please join us if you can. We've had a change in speakers this afternoon, and I'm very sorry to share with you that Dr. Isaac Cohane had a death in his family, and I would like to extend our condolences on behalf of all of us to Dr. Cohane and his family. We do, however, have a speaker who we're very privileged was able to fill in, Dr. Kun Yu. He will lead the discussion on AI, the future of artificial intelligence in medicine. After his presentation, I invite all of you to ask questions. If you're watching through the live stream, please note your questions on the Facebook Live comment section or the YouTube section, and we will get to as many questions as possible. You know, it's nearly impossible to remember a time when technology did not play a major role in our lives. But can we rely on computers to detect a cancerous mole? Or can we use a computer algorithm to discern benign cellular changes from malignancies? The use of computerized medical decision-making has been the stuff of sci-fi, right? But that is rapidly changing, and we're going to hear more about how today. Advances in artificial intelligence and machine learning are transforming our ability to analyze vast amounts of data and to predict outcomes in both biomedical research and healthcare delivery. With so much change underway, can AI help manage the massive amounts of data being collected? And can it improve clinical decision-making, clinical diagnosis, and ultimately, can AI affect your healthcare and how it is delivered? It holds so much promise, yet it is not without challenges to ensure that's effective and reliable as a tool. Our speaker today will describe the progress and the challenges of harnessing data into deep learning algorithms and the promise it holds, how this trend of AI is reshaping the future of medicine. So I'm pleased to introduce our speaker. Kun Yu is currently a research fellow in Isaac Cohane's lab in the Department of Biomedical Informatics at Harvard Medical School. His research interests include translational bioinformatics, machine learning, biomarker discovery for complex diseases, and precision medicine. Please welcome Dr. Yu. Thank you.
Thank you very much for the kind introduction. Today, we are going to talk about a hopefully interesting topic on MD versus medicine, how artificial intelligence would transform medicine. But first of all, some conflict of interest. So we submitted a provisional patent on a pathology AI system to the USPTO, but actually, the biggest conflict for me is that I'm an MD by training. However, I'm a big fan of AI since childhood. So hopefully this double conflict on both MD and AI side will make my perspective more balanced. So for today's outline, we will first talk about some background and historical perspective on artificial intelligence. And then we will dig into some of the background on how the modern AI systems really work. And last but not least, we will talk about how we can transform medicine using our current AI technology to make a difference to our patient and our healthcare system. Artificial intelligence, broadly speaking, is this field of study that attempts to both understand and build intelligent entities. The recent renaissance of artificial intelligence is largely fueled by three different but interrelated factors. The first factor, availability of the big data. Today, if you go onto any major search engine and type in your favorite keywords, chances are those search engines are recording your behavior online automatically. And for example, your search term, your estimated location, your timestamp, as well as your behavior, for example, which click you click through, and how long did you stay in each of the web pages, are automatically recorded and stored in the big database they have. And now, the cost of storing those big data is essentially negligible, such that all of your information might be kept forever. And with the big data, now we also have the advanced machine learning algorithms to help us make sense of the big data. Previously, data analysis largely relied on prior knowledge and built some statistical hypotheses, try to devise a statistical test to refute the hypothesis or to show that we are not able to refute the hypothesis based on the data we have. But with the advanced machine learning algorithms, now it's possible to just allow the machine to learn the patterns within the data to identify the associations without any human supervision. And last but not least, recently we saw a tremendous growth in computation power. As an illustration, in 2018, this piece of computer hardware is pretty prevalent. It's called Graphical Processing Unit, or GPU in short, and it exists in every single gaming desktop owned by teenagers. And guess what? The computation power resides in this piece of computer hardware has the same computation power as a supercomputer back in 2006. In fact, if we hold on to this piece of computer hardware, jump onto a time machine and go back in time to 2006, this single piece of machine would rank among the top 500 supercomputers in the world. So with this advanced computing power, we can now build sophisticated machine learning algorithms to make sense of the big data. This has largely fueled the recent success of artificial intelligence. And there are many successful and high-profile applications for the modern AI systems. Many of you must have heard the game of Go and how computers defeated the best players in the world. The game of Go is invented more than 2,000 years ago in China. And it is a board game consisting of two players. One holds a black stone, the other white stone. The goal is to surround more territory than your opponent. People have been trying to automate and computerize the program to play the game of Go for many decades. But there are several outstanding challenges in doing so. First of all, there are just so many possible moves in this game. It is estimated that there are more than 10 to the power of 170 possible moves in this game. That is 1 followed by 170 zeros. And if we were simply to enumerate all these simple possible moves, we will soon run out of the available atoms in the universe because there are only 10 to the power of 80 of them. In addition, in order to evaluate who is winning and losing the game, we need a really complicated evaluation function. And you might thought of how about us just break this whole board into different regions and try to evaluate this local effect and try to sum it all up. But unfortunately, because of the rule of the game, those stones are connected in a way such that we have a complex interaction among those local endgames. So we cannot simply divide the whole game into different subgames and try to sum up the scores from different regions. But many of you may notice that since 2016, there's a series of success in the field of computer Go. AlphaGo is a system built by Google DeepMind. And in 2016, in an open in an open forum, it defeated one of the base human players, Mr. Lee Sedol from South Korea, by 4-1. And the revised version further defeated all 60 professional players in an online Go forum. In 2017, the system defeated the current champion in Go, Mr. Ke from China. But most surprisingly, in 2017, the developers of this system decided to train their system in a totally different way. Previously, AlphaGo system is largely developed by asking the machine to read the Go literature, to learn the winning and losing moves throughout the 2,000 years of Go history. But in last year, they decided to take on another approach. That is, how about I just build a machine to play against itself millions of times in order to learn the winning and losing patterns on its own. And the system resulting from this new strategy is called AlphaGo Zero. And surprisingly, the system AlphaGo Zero defeated the vanilla AlphaGo by 100-0 games. This might be an indicator that humans might be playing the game of Go in the wrong way for more than 2,000 years. And now we are inevitably being faced with the question on, can machine really think? We get that machine can play games like Go, which that the rule is pretty set. And how about the general intelligence? Can machine really exhibit general intelligence of human? And in order to answer these questions, philosophers and computer scientists have been thought about ways of evaluating this question. And one of the most famous attempts is called the Turing test, proposed by Dr. Alan Turing back in 1950s. And the goal is to evaluate whether the computer system has demonstrated human-level intelligence. How to do so? In this proposal, Turing proposed that we have a bunch of human evaluators to interact with either a human player or a computer player. And through question answering, the human evaluator might be able to get a sense of the behavior or the level of intelligence of their counterparts. But in order to avoid some not so relevant factors like how the machine looks or how they sound, so Turing proposed to use a text-based conversation channel, pretty much like an online chat system, in order to obscure all those not so relevant factors. And in the original proposal, Turing suggests that by the year of 2000, it is possible to build computer programs that will be able to fool more than 30% of human evaluators. And sure enough, in 2014, there's a computer system called Eugene Guzman, which impersonates itself as a 13-year-old boy from Ukraine. And it successfully fooled more than 30% of the human judges in an open computer forum. And this has been thought of as a way of passing the Turing test by some people, although it is still under controversy in that this computer system deliberately impersonates itself as a 13-year-old boy, which may not have a lot of knowledge, and also from a country that is not, that English is not their first language. Okay, so now you might thought that, okay, so machine may be able to exhibit the level of intelligence of a 13-year-old boy, but there's always something that is always in the realm of human. For example, creativity. Can computer really write, say, poems that will have the deep meaning of life? Well, so let's do a quick quiz here. We have two poems here. One is written by a computer program, the other by a renowned human poet. And I will give you 20 seconds to read through both poems and decide which is which. Okay, time's up. And I want a show of hands on your decision. For those who think poem 1 is written by a machine, please raise your hand. Thank you. The majority of them, more than maybe 70% of them. How about poem 2? For those who think poem 2 is written by a machine, please raise your hand. Thank you. It turned out that poem 1 is written by a famous American poet. Whereas poem 2 is written by a computer system called RKCP. So RKCP program has successfully deceived many of you, more than 70% of you, into believing that he's a human, he has this deep understanding of like human life and wrote this deep poem. And alternatively, some people may also argue that Miss Dan actually have deceived most of you into believing that she's a computer. So by the reverse Turing test, we might argue that Miss Dan may actually be a computer. Maybe that's going too far. But how about other creative jobs? Like, can machine really paint? For example, can machine paint human masterpieces, like the three shown here? In order to answer this question, one day I come to my lab server and ask the machine, hello machine, can you take my profile picture as your input and try to generate output that would mimic the human masterpieces that we have in the history here? And lo and behold, after learning the painting patterns of those masterpieces, computers successfully regenerated my profile picture using the style learned from those major artists in the world. And not only AI has this success in playing the game of Go or generating some creative jobs that we once thought to be only in the realm of human experts. Now, in the medical settings, we can train computer systems to behave intelligently and to arrive at the right diagnosis at the expert-level performance. For example, in 2016, a group of researchers from Google has reported this computer system to diagnose diabetic retinopathy, which is a common complication of diabetes. And by looking at the fundus photographs, that is the photograph taken to visualize the back of our eyes, it has arrived at the expert-level performance in identifying the referable diabetic retinopathy patients. And a similar system by another group has been proposed, implemented, and approved by the US FDA. Another application on skin cancer, this is a paper published by a group from Stanford showing that machine learning algorithms can successfully and accurately diagnose many types of skin lesions and skin malignancies with expert-level accuracy. Another research published by radiologists shows that similar approaches can be used to classify and diagnose pulmonary tuberculosis by looking at the chest X-ray films with more than 99% accuracy. So these are all more like image-related diagnoses. And you might wonder, would it be possible to build a computer system that would act like a human general practitioner, taking not just the image as its input, but the overall signs and symptoms exhibited by our patients? And sure enough, there's a group of researchers that built this intelligence consultation program to suggest the diagnosis and treatment options for patients. And the overall program is pretty complicated, but we can simplify it in this diagram. Basically, it's a consultation program built using the human knowledge and embody this knowledge into a database. And they have formulated some inference rules such that given the input from the patient's symptoms and signs, we can arrive at the right diagnosis and treatment plans. And they also conducted a head-to-head study with infection specialists practicing in an academic hospital. And they show that there are 2 to 25%, there's a 2 to 20% of improved performance by comparing this computation program to the human experts. And instead of just giving the citation right away, I would like all of you to make a guess on when was the system being developed. So we have 4 options here. For those who think the system is developed back in the 1970s, please raise your hand. Thank you. Very brave of you. How about 2012? It was around the time like IBM Watson defeated the human champion in the game of Jeopardy. Thank you. How about 2017? Around the time we have this human-level performance in diagnosing skin lesions and fundus retinopathy. Thank you. And how about 2018? Maybe this is some new advance this year that was not popularized by the public media. Thank you. It turned out that this very system is developed back in the 70s, in 1975, as part of Dr. Ted Shorty's doctoral dissertation. So Dr. Shorty has built this expert system to formulate the human knowledge at that time in diagnosing and treating infectious diseases And they have conducted head-to-head study to show that it was successful and have the expert level knowledge and performance in treating human infections. So you might wonder, what's going on here? Why we have a lot of success back in the 70s, but now no one really talk about it, and it's not really implemented in any clinical settings at all. It turned out that throughout the AI research history, people have been attempting different approaches in building an AI system. The term AI is first proposed in 1950s in the computation conference in Dartmouth. And following that, we have several landmark discovery and development in pattern recognition, machine learning, and knowledge representation systems. But in the 70s, something happened. It turned out that AI, as well as other technology, follow this hype cycle. In that first, we may have some surprising technology, and now people have built out more and more expectation on what the technology can do and what it should do. And once the technology fails to follow up with people's expectation, we will be facing an inevitable substance crash. What happened in the 70s is that at that time, expert system is pretty common, and people try to formulate experts' knowledge into this knowledge base to perform some inference that is not so trivial. But at the time of the 70s, the technology seems to be saturated, and now the research field has faced a bottleneck. But for the general public, their expectation is still going up and up to the point that some scholars begin to realize that a lot of proposals written in the forms of, say, academic grants are just not feasible, because the technology at that time could not really support those sophisticated systems with that much expectation. So a lot of funding agencies, including DARPA, respond to the report by that hill. And then in the industry sectors, people still try to build some commercializable applications for the AI at that time. So they built a lot of machine called the LITS machine, which is a specialized computer system for building expert systems. But in the 1987, people realized that actually there's just not a lot of commercializable applications that would be amenable to the technology at that time. So soon, no one continued to buy this machine, and there's a huge collapse in the market as well. So now we might be at another hype of this AI cycle. We now have new technology, and if we are not careful enough, AI winter might be impending, just as the two cycles we've seen in the history. So how do we really avoid the next AI winter? First of all, we need to have a deep understanding on how modern AI system really works and its limitations. And then we will have to know how to address the challenges faced by us to implement this AI application at scale in our clinical settings. So for the second part, I will briefly talk about how does AI work and what is underpinning the current success in the modern AI systems. Throughout the history, there are two major approaches in AI. One is the rule-based approach, and the other, which is driven the recent renaissance of AI, which is machine learning, or more specifically, a branch of machine learning called deep learning. So how do they really work? For the rule-based approach, the underlying concept is pretty simple. That is, in order for a machine to reason like a human, we first need to build a knowledge base to incorporate all the rules that was used by human experts. For example, the rules of making the diagnosis. And after we build this knowledge base, we can draw conclusions by feeding the input data through the rules to arrive at the diagnosis or the treatment decisions. So this is pretty similar to the MySync application we just covered, which was published in the 1970s. But there are several caveats in this rule-based approach. For example, some of the inference rules used by clinicians are just so difficult to formulate. Why is that? Because there are a lot of heuristics that is so common for humans, but in order to spell out what is really inside of that heuristics, it turned out to be a pretty challenging task for computer scientists. In addition, sometimes the clinician may just have a hunch or intuition on what may be going on in this patient, and those hunches are even harder to formulate and formalize. In addition, once we have new pieces of information, in order to update the whole system, we would need to revamp the whole thing, in that for the knowledge base, we might need to encode new knowledge into it, And the new knowledge, the new rules might have conflict with the existing rules, and we have to sort out those conflicts as well. So it's very difficult to maintain and update such system. And that is how and when machine learning came to rescue. Machine learning is widely used in this current AI hype cycle in that it allows machine to learn the non-obvious associations directly from the data, bypassing the human formulation of these inference rules and database. And there are several branches in machine learning. For the interest of time, I will just briefly cover two common forms of machine learning, that is supervised machine learning and unsupervised machine learning. Supervised machine learning aims to look at the data and predict some useful outcomes by drawing the association between input and output as the outcome. And for unsupervised machine learning, it only aims to identify the underlying structures of the data, for example, to detect abnormal data points from the raw data we have. So how does this mean? For supervised machine learning, the simplified algorithm will look like this. In order to build a system, first we need a lot of training data. And with the training data, we can build a machine learning model to draw the correlation between input and our desired output. And in order to validate or to evaluate the performance of the model, we need to input new data and compare the predicted outcome for the machine with the real outcome we observe in our patients. So for example, in order to build an AI system for general clinical diagnosis, we might have to first collect a huge training set. For example, we can collect a symptom to diagnosis data set from electronic medical systems like those from the partners. With that piece of information, we can build algorithms, arrive at the model, and evaluate the model by collecting new data from new patients, such that this new patient is not involved in the process of training the model, so we will have an objective view on how the model really performs. And later we can compare the machine predicted outcome with the actual outcome. There are several approaches in formalizing this supervised machine learning approach. For example, we can simply just plot the data points for those with different diagnoses, the black diagnosis and the white diagnosis, and try to ask the machine to draw this decision boundary that can help us separate the patient with different diagnoses. This is one common way developed in the 80s and the 90s. And more recently, people have been thinking about using so-called deep learning or deep neural networks to draw the association between input and output. The actual model will be very complicated, but in general follow this rule in that we can have some neuron layers that incorporate the information from our input layer, do some mathematical computation, and output is signal onto the next layer. And after multiple layers of data incorporation and accumulation, we can arrive at the final decision that was not so obvious given the input data. And some people argue that this particular approach bears some resemblance to how our human brain works. For example, like now we are taking a lot of input, some visual input, some audio input from our sensory organs. In our brain, there are certain neurons responsible of taking this input, do some function or do some transformation to incorporate this input signal and pass its action potential onto the next layer of neurons. This is basically a simplified model for how our human brain works. And because of the elasticity of these artificial neural networks, now we've seen a lot of success in diagnosing disease and playing the game of Go, as well as other successful applications. For the unsupervised machine learning, there are several well-established and well-utilized approaches. For example, based on the data, we can simply identify different clusters, for example, patient subtypes, without having to know the actual diagnosis of the patients. By the clustering algorithm, we can cluster the clinical profile of the patient into, say, different disease or different disease subtypes this way by just looking at the input data. And we can use similar method to detect anomaly from the data as well. For example, based on looking at the data, we may be able to formulate some form of reasonable data distribution in our input. And with that model, we can identify the outliers, which may be patient with a novel disorder or patient whose behavior or drug response are totally different from the ones we have observed. So to make this more concrete, I will quickly go through a case study, a pathology AI system developed in our lab. As many of you know, pathology is the definitive diagnosis for many types of diseases, including the majority of cancer types. And this need to be performed by trained pathologists, where pathology defines cancer subtypes and types. However, in some of the difficult diagnoses, inter-rater disagreement has been reported in that given the same set of slides, pathologists may not agree with one another on some of the difficult diagnoses. And in order to formulate this problem, we have built an automated image processing and classification system to try to extract objective features directly from the pathology images, bypassing any human labeling of the slides in detail. So in our approach, is a supervised machine learning approach in which we need to collect a lot of data as well as the human annotation on the disease outcomes. And we divide our data into distinct training and validation sets. With this data, we have built an automated AI region of interest selection algorithms to focus on the type of region that may process pathological changes. And we built machine learning algorithms from there. After we build this model, we try to evaluate the efficacy of the model and visualize the model in order to interpret what is going on inside of this AI black box. And here's an overview of the result. Based on this AI system, we have successfully detected tumor cells from lung cancer pathology slide with more than 99% accuracy in our base model. And we can also differentiate the most common subtype of non-small cell lung cancer by looking at the correlation between the patient with different subtypes. And not only we can recapitulate expert pathologists' diagnosis, we can even predict something that is not so obvious to the human eyes. For example, predicting cancer patients' survival is always a tricky process in that it depends on a lot of factors. And it is unknown whether pathology site contain more information than just like staging and grading the patients. And in order to solve this question, we built a computer system to use machine learning to look at the possible correlations between the input raw slide and their survival outcomes and draw any possible correlations from there. And we will validate the hypothesis generated by the machine using the independent test set that was not involved in the data training process. And sure enough, our system has passed our first validation in the first test set, and we further validate the efficacy of the same model in another patient cohort. Not only we can recapitulate diagnosis and prognosis, we can even look into something that is drastically different from what we used to do with the pathology slide. For example, there are several genetic mutation status that are important for cancer patients because those may be indicators of certain treatment response or the patient's survival outcomes. And in this case, because of this set of quantitative features, we can draw the correlation between this set of objective and quantitative image features with their genetic mutation status in order to learn more about the biology underpinning the tumor with different morphology. But there are still several limitations in the current machine learning-based AI system. For example, no matter how fancy machine learning is, it still falls into this limitation of garbage in, garbage out. Suppose our input data it has some systemic bias. Our model would actually learn from those biases as well, in addition to the signals. So the generalizability of the model will largely depend on the representativeness of the training data. For non-medical illustration, there's some startup trying to build an AI system to be the judge of some beauty contest. But guess what? Simply because they didn't take enough time to dig into the historical data in the beauty contest, their data is largely biased in terms of race. Therefore, the machine learning model, although it seemed to be objective, but it contained all sorts of bias and prejudice, and it would just amplify them and recapitulate all those models, all those biases in our training data in the form of models. In addition, the labeling of the cases might evolve over time. For example, there are always some emerging infectious diseases, and if we are not careful enough, those diseases or the patient with those diseases may be erroneously classified as patient with some known diseases. And last but not least, for machine learning-based AI, most models are only looking at correlation, but not causation. So we have to be extra careful in interpreting the model. For example, some of the demographic factors may be a great predictor for patient survival outcomes or any other clinical prognosis. But it's just correlation. It may not be the racial factor that drives this issue. It could be socioeconomic status or other more tricky reason that is hidden inside of our training data. So now we have this deep understanding on the current technology underpinning AI and its limitation. How do we use this piece of technology to transform medicine? There are several approaches people have been proposing. In the conventional clinical practice, we rely heavily on clinicians' judgment on integrating the clinical presentation of the patient, the lab data, and other imaging results to arrive at the final clinical decision and return their judgment and their ways of thinking in the electronic health records. And with the decision support system empowered by AI, we can now build in this AI system into our decision model in that clinicians can input this data into the health records, and then our decision support systems can utilize this data to arrive at the assisted decision and feed this back to the clinicians. So now clinicians will have an additional piece of data for them to operate on. And this can also help them to help the patient to get a second opinion in real time. And afterwards, the clinicians still need to arrive at the final decision in this model. But with the recent progress in the infrastructure in our electronic health record systems, we can now build a better model that is more integrative into the current clinical workflow. For example, instead of relying on what is existing in the electronic health record, nowadays, many decision support systems embedded in some of the modern EHR add-on, they can also actively retrieve additional piece of information from the clinicians and from the patients, and then write the result into the electronic health record on its own. For example, in plotting the growth curve, now they can just plot it automatically and then paste that into the patient's clinical health records. But at the end, clinicians still need to make a final decision in this integrative approach. And several people have been proposing to use a totally automated method by passing any human clinician. And one of the simplified models could be looking like this. That is, now we may not need clinicians in some of the clinical settings and just allow the algorithms to incorporate all the clinical data and make the decision on its own. However, this pipeline is still pretty hypothetical, and there's little success in implementing this system at scale currently because of several reasons. And one of the ways of evaluating whether it's safe to use this automated system in a current medical setting would be to do a head-to-head study to show the performance difference between the AI system and the human practitioner. And this is pretty similar to the Turing test we saw previously. That is, we can have some patient or evaluator on the performance of either human doctors or computer doctors and see if the outcome is different. But here we have to beware of a particular fallacy here, that is the superhuman fallacy. Many of us thought that this is like the game of Go. We need to defeat the best human player in the world in order to claim success for the AI community. But actually, given the current healthcare practice, to contribute to medical practice, an AI system does not really have to perform better than the best human practitioners. If we have a system that have a better than average level of expertise, we can already help numerous patients in various communities in the world. So AI can facilitate clinical practice, not just after when we got a superhuman performance. In the meantime, there are several low-hanging fruit that we can all brainstorm about and try to implement some simple AI system to facilitate the current clinical care. So who will benefit from all this practice? Based on extensive analysis by consultation groups, people generally arrive at these 4 different sectors. First, obviously, for the AI developers, for them, healthcare market is it could be just a big and profitable market, and they can benefit a lot by profiting from it. But for healthcare providers, in addition to like some routine tasks being replaced, actually for healthcare providers, we can improve the efficiency and then allow clinicians to free up their time to focus on the high-touch tasks. For example, if we can successfully delegate the diagnosis of the retinal photographs into the AI system, for ophthalmologists, it's a great news because now they can spend more time discussing with their patients on the treatment plans or spend more time in the operation room, do more operation to help the patients. And for the payers, the AI may potentially help to reduce waste from misdiagnosis. For pharmaceutical companies, we can use AI or machine learning systems to identify novel treatment strategies using the advanced data analytics. But who is missing in this analysis? Exactly, patients. Where is the patient in this paradigm? Well, it's still an ongoing debate whether and how much the patient would benefit from all this AI automation. It's likely that the patient can at least benefit from reduced rate of misdiagnosis and increased efficiency. However, how this value created for AI developers, healthcare providers, or payers gradually trickle down to the patient is still unknown. It's possible that it will just never trickle down. Suppose we don't have the right kind of framework, legal framework or economic framework to ensure the happening of benefiting the patients. And there are several ongoing challenges in this implementation of medical AI. For example, integrating the current AI system into a clinical workflow is still a big challenge. And this is the challenge that hindered the 1975 technology, the MySyn AI system, from reaching the clinical settings. That is, a lot of time, they build this better than clinician system, but they still require clinicians to input every single piece of information into the system in order to arrive at the final diagnosis. And this was a huge disruption to the clinical workflow at that time. So the system was never deployed at a large scale to the clinical settings. And in addition to just a smoother integration, another question is, how do we optimize the workflow such that when AI is not perfect, we can still allow clinicians to catch any misdiagnosis in the system? And from the regulatory point, AI also pose a really unique challenge to the FDA in that because most of the AI nowadays is powered by machine learning, and we know that machine learning can benefit from additional piece of information. So suppose we submit a model for FDA approval, and a week later, we have collected more information from our clinics. So we refine the model to get 1% of better performance. Do we need to resubmit the newer model to the FDA in order to ensure that the new model gets certified as well? In addition, suppose our new model performed on average better than the old model, but for a specific patient subpopulation, we're actually doing worse than the previous model. Should the new model be certified and approved? This is still some ongoing challenge that we need to face. And in order to address this challenge, FDA now proposed a new pre-certified approach that not only look at the final product, but also look at the team that developed the medical AI systems. And in addition, many of the machine learning models, as we know, act like an AI black box because it has some complicated mathematical transformations inside of this black box. And how do we really understand this black box is still some ongoing technical challenge. And obviously, there will be some social legal implications on applying AI to the medical settings in that, in the case of AI malpractice, who should be responsible to the unfavorable result? Would that be the clinicians using the AI? Would that be the developers of the AI system at the beginning? Those are still some ongoing challenges that would require ongoing debate and involvement of a broad range of stakeholders to join this conversation. In summary, now we know there are several medical AI applications on the horizon, But beware of some of the current limitations and the overinflated claims you might heard from the general media or from some AI startup that wanted to get people excited about their technology. And also, machine learning models are just as good as the training data. So suppose there's some systemic bias in the data, we will have to be aware of and address them. And there are many social, economic, and legal challenges ahead. And we need to have an open discussion to incorporate a broad range of stakeholders to join the conversations. So, is AI our destiny? No, AI is not our destiny. We shape our destiny. Thank you.
Does anyone have any questions?
Over here.
I have one question with regards to kind of the medical experts that the machine learning algorithm would have to kind of, if you will, compete against. You know, one could imagine a situation where you have 4 experts and they're all very homogeneous. So, you know, the expert system would have to be working at a very high level. But one could also imagine a system where the 4 experts completely vary so that the expert opinion of the model is very low for the algorithm to kind of beat. How does one figure out what's that right level so that you really are comparing your machine learning algorithm to an expert system?
That's a great question. The question largely involves how do we really identify the right type of question in that some of the clinical tasks, clinicians already have a good and homogeneous performance, and in other cases, maybe not so much. So in order to address that question, we would need to have a lot of discussion with the clinicians to identify the right clinical needs. A lot of research questions may be just for research interest and for academic interest, but there are many crucial clinical needs that could be easily accomplished by some of the simple AI systems. So for example, the plotting of the growth curve, that is a really simple rule-based AI system, but just for some historical reasons, because the electronic medical records are not just amenable to many of these newly developed applications. So people develop those systems still had a hard time of incorporating such easy but useful piece of app into the current system. And there are several ongoing challenges, and there are some more like low-hanging fruit in that with the current technology, we are confident that we can solve them already. But there are several more high-level and more difficult challenges. For example, for terminal cancer patients, how do we incorporate their value, their family care, and other socio-economical factors into formulating a holistic care for the patients? So those questions may need additional evolvement and development of the AI system to really understand the human need and the human value. But again, there will be some low-hanging fruit that we can all work together to make it possible.
We have one up here.
Hi, thank you for your talk. I have a question. Around slide 35, I believe, when you're talking about superhuman fallacy, it seems you kind of mentioned that your AI system has to be better than the average of the clinicians there. It's slightly counterintuitive to me. So one line of counter-arguments could be that with human clinicians, you can argue with them when and if a mistake is made. What was the reason? You can get to the bottom of that. But with these neural networks these days, a key component of training them still depends on the stochastic gradient descent algorithm. So the way you train, you don't deterministically know how it's going to perform in that optimization phase. So when the mistakes are made by an AI system, you may not necessarily be able to pinpoint why the mistake was made. So do you have any comments on those, on that fact?
Yes, so those are all very important questions related to the superhuman fallacy. The point of superhuman fallacy is that in many of the AI systems, researchers all aim to build a killing AI system that performs better than the best human player ever. But in the case of many real-world applications, actually, we only need to serve some of the communities of some of the patients at the level of the current clinical practice or the level that is acceptable in the current clinical practice. So in that sense, any system that may be able to deliver the same or reasonable level of clinical care to the selected patient may be already a sufficient argument in order to benefit patients in many communities. For example, in the rural community, when the specialists are not so prevalent, we can serve that community by deploying some simple AI system and refer the high-risk patient to the major medical centers. So that is one point we would want to make on the superhuman fallacy. And the other point is on the interpretability of the machine learning model. And it is true that for many of the models, because it requires a lot of mathematical transformation to build this sophisticated system to model what might be going on in the input data. And many of such models may not be easily interpretable. And to solve that question, now research communities have been trying to build the machine learning model through some basic rules that is more understandable by humans. And such that if the building block is understandable, the whole system may be complex, but still interpretable. And another approach is that by looking at the final model, we can still try to draw some conclusion by changing the input data a little bit to see how that affects our output, such that we can know which bit of information is more important from the machine's point of view. And those techniques are still under development. And it is worth emphasizing that in order to achieve good clinical adaptance, interpretability is a key in that clinicians, including me, generally don't want a black box model. We need to make sure that the model is safe and understandable, such that when the model is making a mistake, we can go back to check what is going on and build the next version, which is better and safer to our patients. So we got a question from Nepal. The question is, after a model is trained, how can we better share a successful model globally? That's a very important point and an intriguing point in that to achieve optimal adoption and a good uptake of the clinical models, we would like the model to be shared freely globally to ensure this clinical impact. And currently, because of the culture in many of the computer science communities, open source sharing is actually pretty common in that many of the models are freely downloadable from online, and developers can download the newer model and try to refine their system accordingly. And I think for the medical research communities, we can try to embrace similar models in that we can share our research result in a more public and sharing fashion to upload our current algorithm or even models, such that we can ensure a more successful uptake of that model. So some of the general infrastructure built by the computer science community, like GitHub or other code sharing or model sharing infrastructure, may be used for the biomedical informatics or the medical research community in general as well.
Hi, thank you so much for this talk. It's been fantastic. I was just wondering if you could speak a little bit more about how to address biases in the data. And in particular, I'm interested in how to make sure the machine learning algorithms that you're training are not capturing, for instance, racial bias in clinicians and trying to replicate some of the human fallacies and make it better than that.
Sure. Yeah, that's a very good point. In machine learning model is garbage in, garbage out, so the quality of the training data is very important. But how do we really do that? Actually, it requires a lot of thoughts in terms of the study design on how should we really collect the data. So for example, if we only collect the data from some online forum, it may be easier for researchers because essentially the cost is minimal in that we just have to recruit some participants from Facebook or other social media. But at the same time, we are selecting our population in that non-Facebook user may have a different health need than the Facebook users. And in order to really address this issue, it really requires some solid study design in that we would like to have a representative training data. So for example, having a really randomly selected sample from our population would be the key, in that we can try to use a probably smaller data set from a real randomly selected population and compare that with our big data set collected from, say, social media, and see if our model is generalizable to the general population. And the use of so-called small data is now on the rise in that big data generally have some underlying assumption and have some selection in people who really contribute to that data. So by combining the model by the big data and the information we collected from the small data, we will have a better sense on how our model can really extrapolate to the population it was unseen and untouched by our training phase. So there's another question from the audience from Brazil. The question is, what can we expect for treatment for Parkinson's diseases? This is a good question and very specific one. And I guess in addition to Parkinson's disease, many kind of diseases with not so great prognosis or tricky diagnosis also fall into the same umbrella. And generally speaking, we have several data analytics tools that could be utilized by, say, the health insurance payers in order to formulate the right incentive for the patient with higher risk for certain diseases. And for the pharmaceutical companies, they can utilize the technology we just discussed, for example, supervised machine learning and unsupervised machine learning, to figure out what are the potential drug targets or the protein domains that would be useful for developing novel treatments. And I think this holds for many of the ongoing healthcare challenges, including the incurable diseases using the current technology at this point.
We have one question right here. This will be our last question.
Oh, okay. Thanks, Quentin. It's a very impressive talk. So I definitely agree. Like there's a impressive, say, a trend and motivation to put deep learning algorithms into biomedical research. But like my question is, like nowadays, most of the research or the combination between research and biomedical and artificial intelligence are in pathology research, or all these like imaging-based like models. So but there are a lot of like other types of data we have in like medicine area. So what do you think about like is the reason of this like phenomenon? Is that because the model is not good enough for the other areas, or is it because of like data collection is not enough for training a deep neural network?
Very insightful point. So in the recent renaissance of AI, most of the success or most of the popularized success lies into the image-based application. And there's one reason to that. That is because of the neural network systems. People have figured out a strategy called transfer learning, in that we can train a big model that is just generally applicable to the general computer vision task, like differentiating between cats and dogs. And for some reason, if we fix certain part of that model and retrain the model using, say, radiology data, we got reasonable result from the start. And this is largely because some of the basic visual elements are the same for distinguishing dogs and cats from distinguishing, say, a stroke with other pathology from the radiology films. And for other fields, the path forward is less murky in that how we could, say, build a model using Google search data and do some transfer learning to make the model amenable to diagnosing, say, infectious diseases based on their clinical parameters. And this is still something of active research efforts in that some of the basic data element may be identical or similar or transferable. But in many parts of the data, it's just that we don't have a deep knowledge on what the clinical data of a, say, stroke patient should look like versus a clinical data of a non-stroke patient. So this transferability is a bit murky. And this is also a part of the ongoing effort on developing so-called general artificial intelligence, in that suppose we can build an AI system that can help us not just understand the trivial or the simple task we have, but to help us understand the behavior of AI models in general, such that we can use the AI to fine-tune these AI models to better make sense of the data underneath of it. And this is still some ongoing research effort and challenge.
Thank you.
Thank you.
Thank you for doing that.
Thank
Do
you.
we have the tools today to take the existing model that we've got?